Most existing work builds datasets for evaluating the model robustness and generalization ability on out-of-distribution data using adversarial examples and common corruptions. They have found that higher accuracy on ImageNet usually leads to better robustness against different domains. However, most previous studies try to achieve this in a top-down way, such as architecture design, exploring a better training strategy, etc. We advocate that it is also essential to manage it in a bottom-up way, that is, conducting model debugging with the in-distribution dataset to provide clues for model repairing and accuracy improvement. Therefore, in this paper, we provide a detached object editing tool to conduct the model debugging from the perspective of object attribute and construct a dataset named ImageNet-Editing. The ImageNet-E dataset is a compact but challenging test set for object recognition that contains controllable object attributes including backgrounds, sizes, positions, and directions. In contrast to ObjectNet, whose images are collected by their workers via posing objects according to specific instructions and differ from the target data distribution. This makes it hard to tell whether the degradation comes from the changes of attribute or distribution. Our ImageNet-E is automatically generated with our object attribute editing tool based on the original ImageNet. Specifically, to change the object background, we provide an object background editing method that can make the background simpler or more complex based on diffusion models. We adopt DDPM approach to incorporate background editing by adding a guiding loss that can lead to backgrounds with desired properties to make the generated images stay in / close to the original distribution. Specifically, we choose to manipulate the background in terms of texture complexity due to the hypothesis that an object should be observed more easily from simple backgrounds than from complicated ones. We hypothesize that a complex image should contain more frequency components in its spectrum and higher amplitude indicates greater complexity. Thus, we define the objective of complexity as this, where f is the Fourier transform, A extracts the amplitude of the input spectrum. X is the evaluated image. In this way, one can easily evaluate how much the background complexity can influence the model performance. To control the object size, position, and direction to simulate pictures taken from different distances and angles, an object editing method is also provided. To realize the aforementioned object attribute controlling, we adopt the orthogonal transformation as shown the above. However, the result generated in this manner may look disharmonic, lacking a delicate adjustment to blending them together. Besides, as shown in the column 3 of the figure above, the object removing operation may leave some artifacts behind, failing to produce a coherent and seamless result. To deal with this problem, we leverage DDPM models to blend them at different noise levels along the diffusion process. With the tool above, we conduct object attribute editing including background, size, direction and position changes based on the large-scale ImageNet dataset and ImageNet-S, which provides the mask annotation. In contrast to benchmarks like ImageNet-C giving images from different domains so that the model robustness in these situations may be assessed, our effort aims to give an editable image tool that can conduct model debugging with in-distribution data, in order to identify specific shortcomings of different models and provide some insights for clean accuracy improving. Thus, the data distribution should not differ much from the original ImageNet. As shown above, compared to other datasets, our method barely changes the data distribution under both energy, the first row, and grad norm, the second row, evaluation methods. We conduct evaluation experiments on various architectures, including both CNNs and transformer-based models. Other state-of-the-art models that trained with extra data such as CLIP, EfficientNet L2 Noisy Student are also evaluated. With the experiments, we have the following findings. 1. Most models are sensitive to object background changes. Other attribute changes such as size and position can also lead to model performance degradation. 2. The robustness under different object attributes is improved along with improvements in terms of clean accuracy, original, on different models. By this measure, models have become more and more capable of generalizing to different backgrounds, which implies that they indeed learn some robust features. This shows that object attribute robustness can be a good way to measure future progress in representation learning. 3. Larger networks possess better robustness on the attribute editing. Consequently, models with even more depth, width, and feature aggregation may attain further attribute robustness. Adversarial training is one of the state-of-the-art methods for improving the adversarial robustness of deep models and has been widely studied. To find out whether they can boost the attribute robustness, we conduct extensive experiments in terms of different architectures and perturbation budgets. As shown in Figure 4, the adversarially trained ones are not robust against attribute changes, including both backgrounds and size-changing situations. The dropped accuracies are much greater compared to normally trained models. As the perturbation budget grows, the situation gets worse. This indicates that adversarial training can do harm to robustness against attributes. The above figure shows evaluations on 91 state-of-the-art models. To validate that the evaluation on ImageNet-E can help to provide some insights for models' applicability and enhancement, we conduct a toy example for model repairing. Previous evaluation shows that the ResNet 50 is vulnerable to background changes. Based on this observation, we randomly replace the backgrounds of objects with others during training and get a validation accuracy boost from 77.48% to 79.00%. Note that the promotion is not small, as only 8,781 training images with mask annotations are available in ImageNet. We also step further to find out if the improved model can get a boost the out-of-distribution robustness, as shown in the table above. It can be observed that with the insights provided by the evaluation on ImageNet-E, one can explore the model's attribute vulnerabilities and manage to repair the model and get a performance boost accordingly. Thanks for watching.